All right, hey folks, video 2, which is really video 3 for this unit, is about simple harmonic motion, which is the name of the unit, and the kinematics of simple harmonic motion. So, oscillations can have kind of any pattern that they want. Um, it, it can be just like a kind of like an on-off switch is an oscillation, but simple harmonic motion is a subset of oscillations. So simple harmonic motion is any oscillation that produces a sinusoidal graph of position versus time. And it has to do with a specific type of restoring force, which is known as linear. So the oscillations you saw in the first video, the spring and the pendulum, those are both simple harmonic motion, meaning they're both simple harmonic oscillators. So that's why we study them. They're like the simplest of the simple harmonic oscillators, and they're still pretty complex. And so we study them specifically as your like first go around. The thing that makes something a simple harmonic oscillator is that the restoring force on the oscillator is linear. It does not mean that it's in a straight line, because if you think about a pendulum, the pendulum swings in an arc that's basically like a section of a circle. So linear doesn't refer to the motion of the object, it refers to the relationship between the force and the displacement of the oscillator. So there is a linear relationship between the restoring force and the displacement of the object. So if you think back to the spring oscillator, I don't know where I put it, there we go. If you think back to the spring oscillator, there's a linear restoring force. It's Hooke's law, force equals K times X. If I stretch it some amount, I get some force. If I stretch it twice as far, I get twice the force. 3 times as far, I get 3 times the force. So not every oscillator has a linear restoring force. The same thing works with pendulums, although it's a little bit trickier. But for springs, it's pretty cut and dry. As you stretch a spring, the force goes up linearly with the displacement of one end of the spring or the stretch. And so that's what makes simple harmonic motion. We study specifically, springs and pendulums. Now, the equation that gets used least often in your equation sheet is this one, the position function of a simple harmonic oscillator. Mostly important just for me to tell you what the properties are that influence it so that they can see it. So the position is a function of time. This can be horizontal or vertical, or at an angle even, is equal to the amplitude times the cosine of 2 pi ft. And so, you're going to see 2 pi come up more in this unit. And so I want you, whatever curiosity you have with that is probably well-founded. You're maybe thinking like, what does this have to do with circles? And I'm going to show you. So before we get to that, t is the variable that influences where the position is. Frequency determines how quickly that cycles through. So, it might be weird that there's like 2 units of time in there. But they actually are time and inverse time. So seconds times inverse seconds cancels. So cosine of 2 pi ft doesn't have any units. Amplitude's measured in meters, and so the position is based on the units of amplitude. Anyway, where does the 2 pi come from? So there's a proof in your book, but someone made a nice Desmos animation of circular motion. So this is uniform circular motion. If you watch that black dot at the perimeter of the circle, it's moving at a constant speed. Those vertical and horizontal bars show you the vertical and horizontal positions. So let's focus on the horizontal bar that's going up and down. That bar is in simple harmonic motion. So is the vertical bar that's going back and forth. And all of this to say that one way to derive the relationships in simple harmonic motion is to analyze circular motion. So let me see if I can get this right. I think, yep, there we go, the Y's. I can produce this, or this animation can produce this wave as if it's emanating from the circle itself. And this graph is kind of a live readout of, it is a live readout of the location of this black dot in the vertical dimension. And this is sinusoidal. Now, sinusoidal doesn't mean just the sine function, it's any trig function. Sine or cosine would be sinusoidal. And so the shape is what's important, is that there's this like wave shape up and down that happens regularly. So what we're going to do in this video, and really like kind of the skill in this video, I know this is mesmerizing, is to produce graphs of kinematics based on the oscillation of something. And so we're going to do this like live together. And I'm going to have to zoom out a little bit, but we're going to make 4 graphs. We're going to make all the kinematics graphs, position, velocity, acceleration, and then the extension is we're going to make a graph of force. And the nice thing about this is the relationships between the graphs are all the same. Doesn't matter what the oscillator is, it's always going to have this same relationship. So we will do position, velocity, and acceleration graphs. Now, the point I want to make to you is that the starting location of your oscillator is arbitrary, because you can always start the timer at an arbitrary moment. There are y-axis labels, A and negative A being the maximum displacement away from equilibrium. So whatever the oscillator is, 0 is its equilibrium or central point. And then A and negative A are the furthest that that oscillator gets away from that equilibrium length. So if it's a spring, 0 is actually the equilibrium position of whatever's hanging from the spring, right? So I keep like covering up the spring that I'm using. So you know, if I'm like holding this, you can see it in the camera down at the bottom of the screen. If I'm holding this spring, this is the equilibrium position of the spring, or of the spring. And so the location of the mass in reality would be the position of 0 on that graph. So again, it doesn't matter where I start. So we'll imagine a pendulum. Pendulum's like swinging back and forth. To get a pendulum going, you're going to start it at one of the amplitudes. So I'm going to start it there. So it's going to actually end up looking like a cosine graph when we're done, for those of you who are very familiar with trig. Now, there's 4 marks on the x-axis because we're going to do this in quarters of the period. So this is a position versus time graph, and so I'm going to have the time here be the period of the oscillation. So I don't know what the time is, but that's like one full oscillation is going to be there, which means that t over 2 is going to be there. Now those are the only significant points I want to like identify. This is a quarter of the period, this is 3/4 of the period. But what I want you to think about is before we even draw the shape of the graph, this is where it starts. So that's the moment like where I let go of whatever I'm holding. Now, in the period of oscillation, in one period, it has to go all the way to the other end of its oscillation and come back. So I can map this out. By the time it gets to time t, the position is going to have returned to its original position. So wherever it starts at time 0, it gets back to that point at exactly time t. This graph has to be sinusoidal. The other thing is, an oscillation is, there and back again. So at exactly t over 2, this object has to get exactly to the opposite side of its oscillation. Again, it doesn't matter if it's a pendulum or a spring. This one directional motion from one amplitude to the next is for all simple harmonic oscillators. So these are like the important points that I wanted to map out, and then I just need to draw it like a sine curve. So the way that goes, the slope is minimal at each extreme, and then the biggest slope happens like right in the middle of the extremes, right at the equilibrium. So we have that's the shape for the left-hand side of the graph, and then this is the shape for the right-hand side of the graph. So this is a sinusoidal curve, and it's just position, right? There's like nothing really special happening for this other than this graph matches the description or the equation that you saw, the function of x as a function of t. This is what that graph would look like. Now, I could start it at negative a, I'd have a mirror image graph, my other graphs would change, but as I said, the relationships are always the same. So there's two ways to think about the velocity versus time. Now, for those of you who are in calculus or have taken calculus already, you're going to actually find this really boring because you already learned this in calculus. For those of you who haven't done a lot with trig, this is going to be a lot of information to think about. And so you want to maybe watch this video like a couple times. And I know we're at the 10-minute mark, but I think it's worth it to do that. Okay, so velocity. Velocity, or we'll do in blue. Velocity equals the slope of position, of the position versus time graph. So one way to do this is to make a graph that represents the slope of the velocity. That's a calculus idea. So for the calculus students, go think about that. For the rest of us, we want to imagine that this oscillation is happening in front of us. And so we want to imagine, well, where does this object have zero velocity? Well, it has zero velocity when it gets to the extremes. So you can consider this to be zero velocity because you haven't let it go yet. So at time zero, we have a velocity of zero. At the opposite extreme, let's imagine a pendulum. It swings from one side to the other. When it gets to the other side, it actually has to stop before it turns around. And so again, at the t/2 location, it's going to have a velocity of zero. And then when it gets to the original extreme again, it's also got to have a velocity of zero. And so let me see if I have another blue pen. I do not. Oh well. So velocity equals zero at the extremes, because it's the end of the oscillation. It's actually slowed to a stop by the restoring force before it comes back. I just have to get the shape of this graph right, and I can do that pretty easily, right? From t equals 0 to t/2, this is all moving in the negative direction. And so my graph, which is going to be sinusoidal, has to go into the negative first. The second half of the graph goes from the most negative to the most positive. So that's a positive velocity at all times. And so I'm going to have a graph that looks like this. So I'll draw the graph and then we'll talk about it one more time. So the graph is going to have a shape like this. And so, you know, hopefully the easiest part is the velocity of an oscillator is zero whenever it gets to the extremes. In other words, whenever it reaches its amplitude, it actually has to stop because it's about to come back. These velocities are the maximum. So V max, well, look at where that happens. It happens at like t/4. That's when it's passing through equilibrium. And then 3t/4, that's when it's passing through equilibrium. So the maximum velocity happens at equilibrium. As it passes through the equilibrium point, that's the maximum speed it's going to have. Now, there's a force explanation for that when we get to the bottom. We'll come back to that. Okay, so what you do want to also look at is the velocity does represent the slope of this graph above it. So this is the most negative slope in the entire graph. It's the most negative velocity. These 3 points are essentially flat. They're like the top of a hill. And so those are the 3 zero velocity points. There, there, and there. The most positive velocity happens here, and that's the most positive velocity. And so there we are. So we have velocity from position. For acceleration, again, acceleration is the slope, but it's the slope of the velocity versus time graph. So here's the hardest one to do because acceleration is tough. So we're going to rely on slope, and then we're going to kind of work backwards for this one. So the slope at this point is negative because this line is going down. So I'm going to put the most negative acceleration at time 0. This is a slope of 0 because it's at the extreme. This is the most positive slope, so I go here. This is a slope of 0, and then this is the most negative slope again. So I draw a smooth sine curve. And the people in calculus have gone through in their head like what the derivative of sine functions are, and you're like, this is boring, please stop this. But anyway, here we go with our acceleration graph. So what do I want you to notice? I actually want you to notice the acceleration as it depends on position. The acceleration equals 0 there and there when the object is at equilibrium. At equilibrium. Now, why does that happen? That happens because at equilibrium, there is no restoring force. It's the only moment in the oscillation where the restoring force is 0. And so that's, it's neither speeding up nor slowing down. At all other times, it's either speeding up or slowing down because there is a restoring force. So when do we have the maximum acceleration? We have the maximum acceleration when we are at the extremes. So the most negative acceleration happens at the most positive position. The most positive acceleration happens at the most negative position. So the acceleration is at a maximum at the extremes. Now, that's like a lot to take unless you remember Newton's second law. The idea behind the restoring force is it's linear. So the further you get away from equilibrium, the more force there is. And so the furthest point away from equilibrium, there's going to be the most force and therefore the greatest acceleration. So what's kind of paradoxical about an oscillator is that it has the greatest acceleration when it is not moving. And so just kind of like checking yourself and remembering that that's even possible is pretty important. Okay, so to kind of tie everything together, we have a graph of force. The force graph is so easy because the force is equal to mass times acceleration. That means that the force graph should have exactly the same shape as the acceleration graph. So there's no tricky like slope area under the thing or anything. They have the exact same shape. So same shape, different numbers. And I say that like that's important because these graphs look identical, but the maximum force only equals the maximum acceleration if the mass of the object is 1 kilogram. Under all other conditions, they are different. So they're proportional to one another, but not equal. So, you know, you get like the maximum force at the maximum displacement, just like acceleration. So as you stretch, the further away you get from equilibrium, the greater the force. The final thing I want you to notice is that the graph of, if I can even do this, the graph of force and the graph of position, they are mirror images. So think about Hooke's law. The spring force is proportional to the force constant times the stretch, but in reality, the force constant, sorry, the spring force equals the negative force constant times stretch. If the stretch is positive, the force is negative. If the stretch is negative, the force is positive. Whatever the oscillator is doing, the spring is pushing or pulling in the opposite direction. That was a lot to do in one video, I realize, but thank you for bearing with it. And that probably represents our most complicated lesson of the unit. Nice job.